Welcome to this deep dive. Today we're jumping into the Online Encyclopedia of Integer Sequences, the OEIS.
Ah, yes, the OEIS. An incredible resource for anyone interested in number pattern.
It really is. And specifically, we're looking at sequence A000216 today.
A very interesting one. It comes from a surprisingly simple rule.
Right, the rule is just take the sum of the squares of the digits of the number before it, and we start with 2.
Exactly. So starting with 2.
Okay, so 2 squared is 4.
Then 4 squared is 16.
And for 16, that's 1 squared plus 6 squared, 1 plus 36, so 37.
Let's keep going.
From 37, we get 3 squared plus 7 squared. That's 9 plus 49, which is 58.
Right. That 58 gives us 5 squared plus 8 squared, 25 plus 64, that's 89.
Okay, 89. 8 squared plus 9 squared, 64 plus 81 is 145.
Nearly there.
145, 1 squared plus 4 squared plus 5 squared, 1 plus 16 plus 4 is 20.
And finally, 20. 2 squared plus 0 squared is just 4. And wait, we've seen 4 before. Precisely. And that's the key observation here. The sequence becomes periodic, it hits 4, and then it just repeats.
So it enters a cycle. What are the numbers in that cycle again?
It's 4, 16, 37, 58, 89, 145, 42, and 20. It's 8 numbers.
An 8-term cycle. Wow, and it just keeps going round and round that loop.
Indefinitely. Once you hit 4, or even 20, since that leads directly to 4, you're caught in that cycle forever. The sequence converges to this cycle.
That's fascinating. So, the OEIS entry mentions something called the offset. How does that fit in here?
Right, the offset. Well, we naturally start counting from the initial term, 2, so we might say the offset is 1.
Okay.
But the rule itself, summing the squares of digits, is also a sequence, A000218. You can think of our sequence, A000216, as the orbit of 2 under that rule.
Ah, so applying the rule to 2 gives 4. You could almost see 4 as the first term generated by the rule itself.
Exactly. So depending on the perspective, you might see different offsets listed. It's a nuance of how the OEIS catalogs things.
I see. And there's another connection mentioned to sequence A080709.
Yes. It basically says that our sequence, after the initial 2, is identical to A080709.
So A08709 must be the sequence that starts directly with 4.
That's right. It jumps straight into the cycle we found. It shows how these sequences are often interrelated.
The entry also gives a pretty compact formula using PRI notation. A000216 and 42, 24, 16, 37, 58, 89, 145, 2n% plus 8 and 2. It's a bit intimidating.
It does look dense, but it's quite clever. The core idea is that n% 8-bit, modulo 8.
The remainder when you divide n by 8?
Exactly. Since the cycle has length 8, this n% 8 helps select the correct term from the cycle, 42, 24, and so on.
Okay, so that handles the reckoning part. What about the 8 and 2, and the 2 at the end of the list?
Ah, good catch. The list inside the square brackets actually contains the cycle elements plus the starting term 2 at the very end. That 8 and 2 is a neat trick.
How so?
Well, if n's the very first term, n2 is true, which PRI treats as 1. So you get 8 to the power of 1, which is 8. The formula then effectively asks for the index, 1% 8, plus 8, which is index 9.
And the 9th element in that list, 42 plus 145, 2 is 2, our starting number.
Precisely. But if n is 2 or greater and 2 is false, or 0, then 80 is just 1.
So for n is 2, we get index 2% 8 plus 1, which is 3, and the third element is 4.
Correct. And for n3, index 3% 8 plus 1 is 4, giving 16. It perfectly selects the cycle elements using the modulo after handling the special first term.
That's actually quite elegant once you break it down. And the OEIS also lists code in Mathematica, Haskell, Magma.
Yeah, it shows this isn't just abstract math. You can compute this sequence easily. It's very concrete.
Looking at the cross-references, we see A003132, the rule itself, and A000079 starting from 4, but also others like A000218, which starts with 3.
Right, which hints that the starting number really matters. Starting with 3 might lead somewhere else entirely, maybe another cycle, maybe a fixed point.
A fixed point, like a number that maps to itself.
Yes, like 1. If you start with 1, 1 squared is 1, so you just stay at 1. That's a fixed point for this operation.
Okay. And this whole idea, it's not brand new, is it? The references go back quite a way.
No, not at all. Hans Berger mentioned it in his book Ingenuity in Mathematics back in 1970. And even earlier, Arthur Porges wrote a paper in 1945 called A Set of 8 Numbers.
Likely talking about this very cycle.
Almost certainly. It's one of those mathematical curiosities that keeps reappearing. There's even a mention of semi-happy numbers from a 2010 paper.
Semi-happy, as opposed to?
Happy numbers. Those are numbers that eventually reach the fixed point 1 under this iteration. Numbers like ours that get stuck in a cycle not containing 1 are sometimes called unhappy or apparently semi-happy.
So it connects to a broader classification. Riel's 1983 paper looked at iterating these kinds of functions more generally.
Yes, placing this specific example within the much wider study of what happens when you repeatedly apply functions to numbers. It's a rich area.
So thinking about number theory students using the OEIS, what's the main takeaway from A000216?
I think the key thing is seeing how a very simple, almost naive operation squaring digits and summing can lead to highly structured, predictable behavior, a cycle in this case.
It's not chaotic, it settles down.
Exactly. It shows that pattern and order can emerge from seemingly basic arithmetic processes. It really encourages you to explore. Follow the sequence, look for cycles, look for fixed points, ask why it behaves this way.
It definitely highlights the discovery aspect of number theory. You start playing with numbers and stumble onto these fascinating structures.
That's the beauty of it. And the OEIS is like a giant catalog of these discoveries.
Okay, so to quickly recap, sequence A000021 starting with 2 and iterating the sum of squares of digits, inevitably falls into an 8-term cycle: 4, 16, 37, 58, 89, 145, 42, 20.
A perfect example of emergent patterns in number theory. And remember, the OEIS entry itself is the gateway to more related sequences: history, code, the works.
Definitely worth exploring, and it does make you wonder, doesn't it? What if you, say, sum the cubes of the digits, or started with a different number, or even worked in, I don't know, base 12?
Good questions. Would you still get cycles, different lengths? Would fifth points change? That's the kind of thinking this sequence inspires.
Something to ponder. Well, that's all the time we have for this deep dive. Join us next time as we explore another corner of the amazing OEIS.